Thank you for coming.
So what I'm talking about, Hadoop Eagle is more like a full-stack real-time monitoring framework. So why we do this, and how do we do that? So let me share some background of this. We have some very initial use case. So in the beginning, what we want to do is how do we detect the node anomaly? So say, for example, in eBay, we have a lot of nodes, machines. So how do we detect the node anomaly out of so many nodes? That's a problem, right? So at the beginning, we did something like we extract a lot of metrics from nodes like CPU, memory, and disk. And we want to analyze those information and guess what node has problems. But that doesn't work very well. Why? Because we have so many nodes, we have so many metrics. How can we do that? So it's very hard. So we need a smart way which can represent the status of the machine. So for Hadoop, we figure out the way. For example, what is the most used application in Hadoop? That's a MapReduce job, right? So that's why we select a job to be the fact to reflect the status of the node. So what we did is very simple. We have assumption, which is each node within the Hadoop cluster is approximately equal in the task failure ratio. Say, for example, within the node, we have a lot of tasks running, right? So sometimes the task will fail. So if we select the matrix of task failure ratio for the node, that would be very simple. We only have one matrix to represent the node status. So we think that's an easy way to figure it out. So we use a very simple algorithm. One is a node-by-node compare. Say, for example, we have a cluster, but we can compare the node failure ratio across all the nodes. So say, for example, the first graph, the left side graph, we show that we have one node which have a very high task failure ratio than all the other nodes within this cluster. So we can say this node has problems. We don't know what are the problem with the node. It's probably the memory issue, probably the network issue, we don't know, but we definitely know that the node has problem. So that's one algorithm. The other algorithm is that we take the history of one node and compare the current task failure ratio with the historical task failure ratio, right? If this node continuously fail the tasks, then the node has problems. Then we need to correlate the load failure with other metrics like memory or CPU, whatever, right? That's a initial use case. So here is an example. It's a real example we did in the eBay, which you can say in the middle, right? In the middle, on top of the middle, we have a node which will show that a lot higher failure ratio than all the other nodes. So we can say the node has a problem. So it's very accurate an algorithm to do that. And also in the right hand, we have auto remediation tools, which is a robot, which can decommission the node and then recommission the node. But when we continue to monitoring Hadoop, like we face a lot of issues. The first issue is a scale issue. In eBay, we have a lot of nodes, a lot of tasks running every day, and we have billions of audio log events. We have billions of metrics per day. So this scale kind of challenge is very hard to us for build the monitoring application from the scratch. So the other challenge is the use case challenge, right? We need to look at the host. We need to look at the job monitoring across the job lifecycle, and we need to look at the Hadoop native metrics. We need to look at the log, GC log. We need to look at the Hadoop daemon log, audio log. We need to correlate them together. We need to look at the Yarn framework. We need to look at the queue consumption. So a lot of use cases we need to look at. So that's another challenge. So for the scale challenge and the use case challenge, we come up with the engineering challenge, right? Because so many data, how do you, so many variety of data sources, so many data connectors, different flavor of the data connectors. Like sometimes you need to pull the data from the Yarn API. Sometimes you need to ship the log from the nemnode to our system. So a lot of different data connectors. That's pretty complicated. So also we have complicated business logic. We need to join the data outside of our system. And we also need pre-aggregation. We need to build the memory window, etc. So, and also our alert rule cannot be hot deployed. That's a problem, right? Sometimes we need to hot deploy a rule, which operation team find something we can tune the rule, but it's hard at the beginning as well. So, but even with those challenges, we still go with several use cases. One is a job history performance analyzer, which we use a very smart way. We know that white elephant does a similar thing. White elephant load the data per day and process that. But our approach is very different. Our approach is more like we continuously crawl the data, crawl the job data, job history data, immediately after it's completed. So that means we can get the job data, job status in near real time. It's not the real time, but it's near real time. So from this information, we build a model to monitoring the node anomaly as well. So another example is the job real-time monitoring, which is more like job is running and the job is consuming the resources like CPU memory, right? We can get the information from the Yarn API, and we can slice the consumption for every minute for the job. Then we can figure out the trend of the job, how much memory used during the life cycle of the job. So that's a pretty much cool features which user can find which job has something wrong with that, which job is harm, which job doesn't have any progress within like 15 minutes. So we can get those alerts. Also, we did something for the GC log. GC log is more like we can correlate to GC log with some issues in Hadoop, right? Because GC log is something we can figure out how much post time within a time window, right? And when or how frequency of the full GC. So that's also very important for us to look at the Hadoop performance. So that's the use case we built. But while we build this use case, we think that it's not scalable for the solution because without a framework of how do you specify the rule, how do you get the data, and how do you query the data, it's not possible for our project to be successful. So that's why we want to figure out the framework to do the monitoring. I know we have Legos, we have a lot of like Zabbix to monitor, but those tools just assume that your data is ready. But in fact, everyone to the monitoring will know that we need to prepare the data. We need to have a very complicated logic to process the data and then fit into Legos. And yes, then Legos can do something. But for us, it's very different. So how do we do that? First, we just follow some program paradigm, and we collect data, we normalize data, we pre-aggregation data, we query, we do the alert rule setting, this is like a pipeline we follow. This is a paradigm we follow. But because of so many use cases, we have to figure out a way that we can create a framework for each of the pipeline. So that's our why we want to abstract our application into framework. So Eagle as a framework, we want to do is, firstly, we don't assume data source. We cannot assume data source, right? Data source is a variety of data sources. So we cannot assume the business logic, complex business logic. So that will be important because some type of monitoring system would assume that your data could be like a data source, and you do some the pre-aggregation, and then you join some outside data. So you have to follow those pipeline to do the business logic. But in fact, that's not possible in reality. So also we need a policy engine implementation. So what we did for Eagle is we just several pieces. We create a framework on top of the within the several pieces. One is like we have an API, which is a secure-like API, which will very easy for the front end to develop without the backend support. Also, we have very high-performing query framework. We have a streaming process API, which user can define their business logic graph. That streaming process can on top of Storm and also can on top of a single process as well. So we also create a framework which you can extend your policy engine. Today we have a CP engine embedded in the Eagle, and also we can have another engine as well. So also for the rule evaluation, that's also a framework we need to work out. Why is that? Because our system is working on the streaming environment. And if your rule cannot be scalable to execute it on different nodes, that would be a problem. So that's why we need to abstract the rule evaluation distribution. Also, our first citizen storage is the HBase. On top of HBase, we build several optimization for the query, because in the monitoring system, we need a query, we need a dashboard. So that's why we did that. And also, we most like to modeling our event processing to be metadata driven. So that's pretty important. You need modeling your event to be a generic type, and then the policy engine can evaluate that. So that's the overall architecture of the Eagle. That's pretty straightforward. From left side is the data source, and then data source mostly will go to the Kafka. That's a messaging bus. And also we have a streaming process engine. We have a DSL you can specify the graph of the execution. And also we have a metadata manager, which you can initialize your metadata, and then everything is driven by the metadata. So that's pretty important. Yeah, data storage, we mostly use the HBase. So let me talk about a little bit about part of our framework, which is a lightweight streaming process framework. Sorry about so many words here, but the fact is that in the monitoring system, we need to compute a lot of stuff, right? And the computation is based on the single events, right? You have a single event, and also you have a window of the events. You need to compute against the window. So at the beginning, we don't use the Storm. We don't use any data processing streaming framework. And we want to use some design pattern to resolve this issue. And because we have so many pieces of code, how do we organize those code, right? So eventually we figure out, we look at like a cascading, right? Cascading is more like you can define your execution graph, but cascading different is that cascading interpret your code into the MapReduce job. But our code should be running within the streaming environment, so that's different. And also, streaming process is a DAG, is a graph. Why do we need this layer of the streaming process? That's pretty important. So, for example, we can use the storm, right? We can program it with the bout or spout with the storm primitives. But we don't do that because we want our system to be portable. Like you can run a system within a single process. You can run on the storm. So that's why we have a very lightweight abstraction of data processing, streaming processing. So that's for the data processing part. We have two steps. One is you need build the dependency between your tasks. That's very easy. Use Java DSL to specify the dependency of your task. And then the second step is you need to specify the protocol between the tasks. That's very important because in a single process, you need mostly you exchange your object with object reference, right? But in the Storm environment, that's different. That's distributed. So in Storm environment, mostly you use the Storm protocol. Storm initially used the 0MQ. Today, it's used the Leti to exchange the data. So you need, in step 2, you need to specify the data exchanger protocol. So that's what we did is in the left side, your code and your code with the streaming executor. You implement the streaming executor. You accept the event. You process the event and ask the framework to collect the event. And after step 2, you specify the protocol. Then if you specify the Storm protocol, then it will, in the runtime, it will be run as a Storm topology, which is like a spout and bout. And also, say, for example, here, we can have a bout. And this bout probably consists 2 different tasks. That's sometimes to optimize your process. Instead of always use the bout to communicate the data across network, you can also restrict the data exchange within the single process. That should be much easier.